I'm happy to have us with us on the stage today, Mark Seemann. He's been in Cluj. Initially, I said for the third time that, but I was wrong. It's the fourth time that Mark is in Cluj, attending our events. And I have the feeling that he's enjoying being part of our community, so he's definitely coming back. Every time I've seen his talks, I got the trigger to check some things that I already knew. I almost always practiced. I almost always advised others to practice, and yet I felt that something is missing. And it was always a good opportunity to revalidate and recheck the way I was, approaching that particular topic. And while today's presentation it might be a bit more, metaphorical or more metaphysical, if you want, I'm sure that is going to have the same impact on not only me, but also on you, and is going to force you into revalidating and rechecking some of the things that you're already knowing and already doing. With that, I think I spoke enough. Enough people have stepped into the room. So please join me in welcoming Mark for the second time today on the stage. Mark, the stage is yours. Thank you.
Yeah, so good afternoon, and thank you for coming, everyone. My name is Mark Seemann. You already know that. If you want to know more about me, there's information on that web address there, blog.play.dk, so I'm not going to bore you with that. So it's good to be back in Cluj. Unfortunately, I have to leave after this pretty soon anyway, so family emergency thing, and so I'm sorry that I can't hang around. I'd really like to do that, but anyways. So I'd like to talk about epistemology of software. So as you can tell, not only is it a difficult word, it's also difficult to pronounce. I've been thinking about that word for many years now, but I'm not that trained in actually pronouncing it. So I may get it wrong as well as I just did there. And I'll explain what that word means in a while, but I'll do something else first, and then I'll come back to what epistemology means later on. All right. So I've noticed that there is a theme that seems to go through a lot of the things that are happening on this conference, and also just in general. There's been a lot of talk about large language models like ChatGPT, and what they can do for us and what that means for the future. Now, I'm not really using ChatGPT because I'm using an alternative tool or an alternative large language model called GitHub Copilot. This one is specifically for assisting you with writing code, whereas ChatGPT is more like a general purpose large language model that also happens to be fairly good, apparently, at writing code, at least simple code. So people use it to write code, and you can also use something like Copilot to write code. And that raises some questions, and obviously maybe the most immediate question that comes to mind is that going to replace all programmers? And I hope not, because I'm a programmer and I'd like not to become obsolete, but on the other hand, I actually don't know. That's not really the question that I want to tackle here today, but rather another adjacent question to that, and that question is if you are using large language models to write software, how do you know that it actually works? Because this notion of maybe being able to replace programmers with large language models, it seems to imply that you will have someone who doesn't know how to write code, or someone who doesn't know how to read code. You would have those people asking the large language models to write the code for them. But then how do they actually know that the code that the large language model is going to produce, how do they know that it's actually appropriate, that it's useful? Because I've noticed, using GitHub Copilot, for example, is that it makes suggestions, but at least half of the times those suggestions are actually not good suggestions. Now, it gets stuff right enough times that I keep using it because it's maybe 40, 60, so 40% of the times the suggestion is actually really useful, and then the other 60% it's not really. And I suppose you can improve that ratio over time so that it becomes more and more accurate. So again, I'm not using this as an argument of saying that we programmers need to stay in the loop. But it made me realize something, and the realization is that you need to be skilled in writing code in order to be able to evaluate whether the code is actually appropriate. So this is what I want to talk about, but actually I don't really want, I don't specifically want to talk about it in the context of AI or large language models, whatever we want to call it, because if you think about this for a little while, it turns out that this problem is exactly similar to the problem that every non-technical person have had for the last 80 years, and that is, if you use programmers to write software, then how do you know that it works? If you're not a programmer yourself, or if you're not looking at the programs or the code that the programmers are producing, how do you actually evaluate whether or not it works? So that's the question that I'd like to try to address here today. How do you know that any software works? So we don't really care who produced the software. That's fairly irrelevant to this particular question. But then, how do we actually figure out, is the software useful? Is it doing what it is that it's supposed to do? So that's the question that I'd like to address here. So I think the answer to this question is to look outside of software development and just in general asking the universal question, how do we know anything at all? So this is the, you're laughing, okay, but I'm dead serious here. That's actually what I'm going to do. I'm going to take a detour, and that detour is going to take like half an hour, and I'll talk about how do we know anything at all. We know what works in knowledge acquisition and what doesn't, and then it turns out that the things that we can pick up from the rest of the universe, if you will, that actually applies, those techniques apply to software development as well. So I'm going to bring it back, but I'm going to take this detour around, how do we know anything at all? And we can start with, radical skepticism, if you will. So you probably, run into this quote, all I know is that I know nothing, usually attributed to Socrates, even though if you read through all of Plato, Socrates never says that in any of the, Platonic dialogues, and there's no other recorded evidence that he actually said, that exact quote. But, as it is often the case with good quotes, you just tend to, glue them on to somebody who might have said it and then say, oh, that's great. If you ever try to look up all the quotes that Winston Churchill had been attributed to, it's like half of them, he never said that, but there's just like, they sound like something Churchill might have said, so there we go, Winston Churchill. As they say, 50% or 90% of all information on the internet is false. Quote Winston Churchill, and usually it's Abraham Lincoln, but anyways, doesn't really make sense, right? So that's a really radical kind of skepticism where you say, okay, we don't really know anything at all. And I'd like to explore that notion using another person than Socrates. So I'll fast forward a couple of thousand years to 1619. So what happened in 1619? So an army officer locked himself into a room, nice cozy room with a hot stuff going on in the winter, and he proceeded to have some very interesting thoughts. And that army officer was René Descartes. And René Descartes is a person who had a lasting impression or lasting impact on his on all these things that happened after him. So we still refer to him today, even though you might think, okay, so what has René Descartes actually done for me recently? But one of the things he invented was the coordinate system, and you probably run into those on a fairly regular basis. So he actually had lasting impact on the world. Now, he had a lot of ideas in 1619 when he was still working as an officer. This was before he became sort of like a full-time philosopher, if you will. He had a lot of ideas back then, and it took him some time to write some of them down. But in 1637, he published a work where he was trying to examine, what is knowledge, what's the source of knowledge, probably a lot of other things as well. And in that work, you have this famous quote, cogito ergo sum, which is Latin, and if you probably heard that already, but it means I think, therefore I am. So you probably heard that quote, but have you ever reflected about what it actually means? Because it seems a little bit opaque. I think, therefore I am. What does that actually mean, and why is it regarded as such a breakthrough thing? Why is this important? So I'll try to outline that very quickly. So Descartes was interested in epistemology, which is basically the investigation of knowledge. So he was interested in figuring out, how do we actually acquire knowledge? What can we know? What can't we know? And how can we distinguish between those things? And it's important to realize that, for thousands of years, you'd have this paradigm where you'd read in old books, and whatever the old book said was the truth. So, you'd often read Aristotle, and if Aristotle had written something in one of his works, that was the truth. And some people might refer to the Bible and say, okay, it's in the Bible, that's the truth, and things like that. You get the idea. And Descartes thought that, maybe that's not really a source of truth, because there's a lot of, odd things going on, in the ancient Greeks, for example. So the ancient Greeks, for example, believed that, all matter is made up of, water, earth, wind, and fire, which is like an expanded pop group later on, but anyways. But if you think about that theory for a little while, all matter is made up of those 4 elements. It seems quite absurd, doesn't it? So, but still, no one really questioned that notion. So you had all of these funny things going on, and at the, around the middle of the second millennium, people were starting to realize, maybe this is not really the way to acquire knowledge. We can't really trust those old things. They might actually be wrong. So he discarded the idea of truth necessarily being handed over by old books, and then he started to try to remove all sorts of other things that might, enable him to acquire knowledge, because he thought, okay, that thing's not going to work either. So one of the things that he considered, was, can I trust my senses? If I see something, or if I hear something, or if I feel something, is that a source of knowledge? Is that truth? And he dismissed that idea, maybe a little bit surprisingly, but the reason for that is that he said, well, maybe the devil is producing illusions, so I'm seeing things that are not there, or I'm hearing things that are not there, or something is happening to my sensory apparatus that I can't really trust. And this may seem like an odd notion, but that was basically part of Catholic, Roman Catholic dogma back then, is that the devil was a, source of illusions, and so you couldn't necessarily trust your perceptions. So he keeps throwing away all sorts of alternative ways where he say, okay, so can we gain knowledge from seeing things? No, we can't, because the devil might, make me imagine things. Can I get knowledge from touching things? No, again, same problem, and so on. So he keeps throwing away all of those ways where he may gain knowledge, and the only thing he's left with then is he says, well, I think, that I know, and that's the proof that I exist. So that's where that comes from. And it takes about, a couple of years. It's very early on. What may be history's first, well, actually, Pierre Gassendi, another thinker, comes around and says, well, actually, you can't really know that it's you who's doing the thinking. Maybe you're just the dream of God or something like that. So the only thing you can really say is that thinking is occurring. So the point here is really that we are left with all that we know is that we know nothing. So the reason why I want to spend a little time with this is just to, if you have an illusion that there's such a thing as certain knowledge or universal truth, if there is something as universal truth, it is unknowable. And otherwise than that, there is no certainty. So every knowledge that we try to acquire may be provisional. We have to always, be skeptic about, what that means. So that turns out to be quite an important realization. All right, so if you think that all this stuff about the devil is fanciful, this notion that we can't trust our senses just keeps coming up again and again, in popular fiction like The Matrix, for example. I'm sure that I'm not spoiling it for anyone who says, well, it turns out in The Matrix that all the people are living in a computer simulation. And not only is this a popular idea in fiction, way before that movie, but it also turns out that this is actually something that, real scientists are, sometimes considering, because there are things about the universe that seems to be so, strangely fine-tuned to, enable, just matter to exist, that it's a little bit odd. So it seems like someone has fine-tune the universe, and if you don't believe in God, maybe you can say, yeah, maybe we live in a simulation. So there are people who think that. Anyways, the point is that we can't necessarily always trust our senses because, some people are sick, they hear voices that are not there, and they typically don't realize that that's actually not, it's just happening inside of their brain. It's not something that happens in reality. And in general, we can regard, our sensory apparatus as basically, so Donald Hoffman, there's a cognitive psychologist called Donald Hoffman that says, our cognitive apparatus is basically just a user interface on the real world. So it is not a depiction of the real world, it's just something that enables us to engage and make use of the real world in a way that is good enough that we can survive long enough to have offspring, and that's basically it. But there are lots of glitches in that user interface, in that sensory apparatus. We have lots of things where our sensors, our senses can deceive us in various ways. You can search for lots of optical illusions, for example. This one is a fairly simple and famous one. I don't know if it renders very well. Yeah, it looks okay on a big screen. But the point here is that the vertical bar there in the middle is actually the same green all the way through. But it really looks like it's a gradient. It looks like it's darker on that side and lighter on the other side, even though it's actually the same. And the reason is the background is a gradient, but that causes our brains to interpret things in different ways. And you can just think about some recent internet memes like the dress. The thing is the dress yellow and is it dress golden and white, or is it what is it, black and yellow? I can't remember. Or, the Laurel versus Yanni audio, illusion as well. There's lots of those things that, just indicate that, yeah, maybe we can't really trust our senses too much. We should be a little bit careful with that. Okay, let's put that aside for now and come back to this word, epistemology. Now, epistemology is, as a lot of other things that sound like that, from Greek, and it's made out of two words. So the first one is episteme, and basically just means knowledge, although, the Greeks would write it like that instead because they use funky letters. And then you smash the word episteme together with logia, and that means discourse. So basically, this just means the discourse about knowledge. So it's the study or the science of knowledge. That's all it really means. So that was what Descartes was really interested in, and that's also something that interests me in general. I'm in general interested in, how do we acquire knowledge? So that's why I'm taking this detour here, because I think there's some important insights to be had. And then we can also apply those insights into how do we know stuff about software. Right, so I promise I'll come back to that question, but not quite yet. I have some other things that I want to cover first. So how do we know anything? I'm sticking with that topic for a little while longer, okay? So in order to answer that question, we need to be able to investigate, what is the source of knowledge? Where does knowledge come from? And if you go back again to the paradigm of the ancients, so that would be your Socrates or your Plato or Aristotle or even Descartes, they were working inside of a knowledge acquisition paradigm or regime that we might call introspection. So basically the way you do this approach knowledge generation is that you come up with an idea, and then you just start arguing that idea. And this is famously what Socrates is doing in lots of Plato's dialogues. He has some sort of idea, or he has a question that he'd like to have answered, and then he just engages in some sort of in a discussion with other people, and he argues some things, and then sometimes he arrives at a conclusion. But what often happens in Plato's dialogues actually is that they end in what I believe call aporia, which means basically no conclusion. We're none the wiser than when we started out. But then Aristotle seems to have a more approach to this thing where he actually wants to arrive at a certain point. And this is what leads you to the theory that there's water, earth, wind, and fire. Those are the four elements of all matter, or that you have the five humors or whatever it is. The theory of medicine, which is also completely bonkers, because it turns out that introspective knowledge acquisition paradigm leaves no room for actual experimentation. So for thousands of years, people are having these very sophisticated thoughts, and it doesn't occur to anyone to actually try to test whether the theory actually holds, which is really odd, isn't it? I am already here going to plant a little bit of seed of what's coming. Does that remind you of anything in software? You just come up with an idea and think, yeah, that's probably how it works. And does that work for you? Okay, let's get back to that later on. So Descartes actually had a degree of success, and the reason why he had so much success that he could have lasting impact, like inventing the coordinate system and other things, was that he was working in the realm of mathematics. And mathematics is a little bit special because this is actually one of the few fields of study where this introspective knowledge acquisition paradigm actually works, in the sense that in mathematics you can start out with just an idea, and then based on that idea you can argue your case and you can develop a theory of mathematics. In mathematics that actually works. So what you typically do is you start with some general ideas that seem reasonable, and then you use those things to prove anything else. But the starting points, we call those axioms. They look like theorems, but they're not, because they can't be proven, and instead they just need to be taken as face value. So again, we don't really know if a mathematical theory is correct, because we can't really prove the foundations. We can't prove the axioms. And if you're wondering about what would be an example of an axiom, in geometry, for example, one of the axioms of geometry is that two parallel lines are never going to cross. And again, when presented with such a claim, you'd probably say, yeah, I'm willing to believe that. That sounds reasonable. Two parallel lines, yeah, they're never going to cross. Okay, let's proceed to develop a theory of geometry based on that axiom and a few other ones. So you can do that, and that's what Euclid did back in the ancient Greece. But it always bothers mathematicians that they have stuff that they can't prove, because they don't really, they can't be sure that the theory actually works. So other mathematicians have tried to prove this particular idea, and one of the ways you can try to prove that is by something called proof by contradiction. So that's a well-known mathematical method of proof, where you start by saying, let's assume the opposite, and then we'll try to, through a series of arguments, we will then prove that leads to something that is impossible, that leads to a logical fallacy of some sort, and then you can conclude that the assumption was incorrect. So people tried to do that as well with this one. They said, okay, let's assume that two parallel lines may actually eventually cross, or they may be able to cross each other. And then they proceeded to develop a branch of geometry, and what they wanted to prove was that led to some inconsistencies, so that they could then conclude that this turned out to be true, that the axiom, the idea that two lines can never cross, is true. But what happens is that they never, the opposite assumption never leads to an inconsistency. What actually turns out to happen is that you develop another theory of geometry on various different curved surfaces. So for example, you may develop a theory of geometry on a sphere, where parallel lines actually do cross, in the two poles. So, who knew? So in this case, it turns out that axiom is actually not entirely correct. It is correct in 2D geometry, in geometry in the plane, but it's not necessarily correct in 3D geometry. So again, the point is, you can't necessarily just use introspection as the way forward. You need to have some sort of evidence from other places. What's the source of knowledge? So you'll notice that, in science, technology, and engineering, and mathematics, in that quarter there, mathematics is the odd man out, because it actually works from introspection, but the other fields of studies, they don't. And what I'd like to point out here is that mathematics is not a source of knowledge. Mathematics is a very useful set of tools that will take knowledge produced somewhere else and enable you to transform it and to draw conclusions. So this is why you see, that science and technology and engineering uses a lot of mathematics, because they have knowledge from somewhere else, from observation, and then they can use mathematical models to manipulate and gain insights into those observations, but that's a different thing. So, mathematics is not really a source of knowledge. It is just a tool to manipulate knowledge, which is not entirely the same thing. And just to come briefly back to software development, this also gives us an insight in whether or not we can prove programs correct. Because, if you ask, various different computer scientists in departments and universities, or if you ask, I'm sure a lot of you actually do have degrees in computer science. Some people may run around with a notion here that computer science is a very mathematical approach to software development, and one of the things that computer scientists are trying to do is it's trying to figure out how to prove programs correct. I'm not sure that this is so much a research program anymore, but it used to be a huge research program driven by people such as Dijkstra, for example. It's Dijkstra, Netherlands computer scientist. But the ironic thing is that we should have known already that that's not possible. We've known this actually from before the computer was invented, because Kurt Gödel published his incompleteness theorem in 1931, I think it was, and then in 1933, Alonzo Church comes by and basically puts the nail in the coffin that is called das Entscheidungsproblem. So that's German and means the decision problem, which is probably the vaguest name of a mathematical idea that I've ever heard about, the decision problem. So it sounds much cooler to say it in German, das Entscheidungsproblem. Now it really sounds like you know what you're talking about. But anyways, and not to go into the mathematics too deeply, but then, in 1936, Alan Turing comes around and basically proves the same thing once again. And usually you don't really get credits in mathematics if you prove something that other people have already proven. But, he still gets an honorable mention by the way that he does that, because he basically, hypothesizes something, a machine for general computation, and this is what we later on, called a Turing machine. So he didn't call that himself, obviously. But that's a Turing machine. And it turns out that the way that he describes things, we can make the general, the following general inference. If we want to have a general purpose programming language, it needs to be what we call Turing complete. That basically, that's just another way of saying that we can do, bloody well whatever we'd like to do in that programming language. So that's a useful characteristic of a programming language. But then what these three people then, demonstrated back in the 30s was that if you have a Turing complete system, you can't, there's no general purpose algorithm that will prove it correct. That's not possible. So that's not really a source of truth. Mathematics is not really a source of truth. So we need to look to other sources and figure out, okay, how do we do that if we can't rely on mathematics? All right. So basically, to summarize so far, introspection does not really work. This idea about just starting from, just some sort of idea and then just trying to argue from it, it has flaws. Sometimes in mathematics it produces something useful, but in general that's just a very uncertain, way to try to acquire knowledge. So what we can do instead is we can look towards science, technology, and engineering and figure out how do those fields actually acquire knowledge. And they do that via empiricism. So basically, you make observations of the world, and then you start to draw some conclusions from that. So just to be clear here, this means we're now doing a little bit of a gamble, because Descartes said, well, you can't trust anything, you can't trust your senses. And then now in this empiricist realm that we're now entering into, we're basically making the bet that in general, we probably can. So we're gambling that we can trust our senses, even though we know that that is actually also not necessarily entirely solid foundation. But let's see where that leads us, and in general, this tends to lead us to a useful place. So people were already doing that around the time of Descartes, actually 100 years before. This is Galilei, which you can almost read on the text there already. And he lived in Pisa, and one of the things that he suggested was an experiment where he said, well, what happens if you drop two objects from the Tower of Pisa and then observe what happens? Now, what happens if you drop let's say two balls from the Tower of Pisa? Well, you're probably going to get arrested, right? Because there's a lot of people there, and you don't want to drop things in the head of people. But anyways, but the idea is generally this: if you take two objects, let's just make them spherical for the sake of argument. So let's take two balls of different sizes, but of the same material. So you can imagine that this is made of steel, steel balls, or maybe marbles or something like that, fairly dense material. And obviously, because they're made of the same material, the larger one is going to be heavier than the smaller one. Now, Aristotle would say that if we drop them simultaneously from a height, the heavier ball will fall faster than the lighter ball. And Galilei was not entirely convinced of that. And you know what happens if you actually make that experiment, right? If you drop the balls, they just fall at the same speed. All right, so that's an empirical observation, and maybe we can learn some stuff from doing things like that. So if you do things like that, if you observe the real world for enough times, you may start to form, your brain is really good at pattern recognition, so you may start to form a model of how things work. You've noticed the same thing happening over and over again, and you go, that's interesting. I think I'm starting to understand that there's some sort of regularity involved here. So maybe, if you keep on, observing, the real world, you start to form a model in your brain where you say, okay, not only do I now feel that I understand things so well that I can explain what's happening, but I actually feel that I can understand it so well that I can start making predictions about it. So I'll say, okay, not only can I, explain that two, objects fell at the same time, but I can actually also start to predict that that's going to happen again, and maybe also how long it will take, and so on. Now, if we do that, it is really important that we do make the predictions in such a way that they're falsifiable. So what does that mean? So basically, falsifiable or falsification means that we should make predictions in such a way that we can prove them wrong. Because we're coming back to this source of knowledge. We've already established that we can never prove anything right. If there is such a thing as universal truth, it eludes us. There's no way we can prove things right, but we can prove things wrong. So that's the next best option that we do have. So what examples of that? So a falsifiable prediction might be the Aristotelian one, for example, where Aristotle would say the heavier ball will hit the ground first. And this is easily falsified in the sense that if we make that experiment, we will notice that that's not going to happen. So we can say, yeah, that didn't happen. We just observed that it didn't happen. So even though we can't prove things correct, we can certainly disprove things. So this is a fairly well-known asymmetry in logic, is that universal statements are really difficult to prove, whereas it just takes one counterexample to disprove something. So that's what we're doing here. Now, we could also, put it the other way around and say, we can say both balls will hit the ground at the same time. This is also falsifiable because you could imagine that if you lived in a world where the Aristotelian laws of motions were in effect, then, your observations, your experiment would actually falsify this other statement. But because you live in this world, that doesn't happen. So even though you try to perform that experiment again and again and again and again, you never falsify that prediction. And every time that happens, it gives you confidence that maybe that model that made that prediction is correct. It's not a proof, it's just you're building up confidence. All right? Now, what are some examples of things that are not falsifiable? So this is my favorite example. Capitalism will eventually collapse. So you can imagine that you have a friend who's a communist, or maybe you yourself are as a communist. But if you imagine that you're talking with someone who's a communist, this is old Marxist dogma: capitalism will eventually collapse. And the problem with this is that it's not falsifiable, because I can have a discussion with a communist friend, and he will say, well, capitalism will eventually collapse. And then I'll say, well, but it's been around for a couple of hundred years, so it looks like it's not going anywhere. And he said, yeah, but eventually it will collapse. And then, we could meet up 10 years later and we'll have this discussion again, and I can say to him, capitalism is still around. And he'd say, yeah, but eventually it will collapse. So the problem here is not, I'm not actually trying to harp on, communists or anything, but the problem with this, prediction is that it is too vague. So often we can take things that are, not falsifiable and we can rescue them in some way. But here's another example, and then we can talk about how to rescue these things. But here's another, prediction that is not falsifiable. We can say a drop ball may levitate. Now, you can imagine that I have, a little ball, a little, marble or a little glass bead, and I just hold it out in my fingers here, and then I release it, and you would expect it to fall to the ground. But that does not disprove that particular, prediction, because the person making this prediction just says, well, it may levitate. Okay, so I'll take my glass bead there, and I'm going to hold it out and release it, and I'm going to do that 1,000,000 times. I'll probably get a robot to do that for me, and every time I'm going to observe what happens. And after 1,000,000 times, it always drops to the ground. I can go back to the person and say, well, now I've done this 1,000,000 times, and the person will say, yeah, but the next time, it might, And this is the problem. This is the problem with, you can't prove things in general. You can't prove universal truths. So that doesn't work. We can rescue these things by making them a little bit more concrete. So we can say, if you release a glass bead 1,000,000 times, it's going to levitate at least once. If you make that prediction, we will probably be able to falsify that. I've actually not tried, but I would guess that that's the case. And we could also say with capitalism, we could say capitalism is going to collapse before 2030. Well, it's going to take it some time before we can actually get the verdict on that prediction, but we will eventually get there. So that would make it falsifiable. So that's the thing. All right. So being able to have those falsifiable predictions is a cornerstone of acquiring knowledge. This is really important. So if you have a model that is so accurate that you can actually do that, we often call that a hypothesis, but I'm just going to stick with the word prediction from now on. So once you have a prediction, you can perform an experiment in order to see whether the prediction actually holds. You can observe the outcome. What often happens is the first time around, the predictions don't quite line up, so you have maybe to go back and adjust your theory a little bit. You may, for example, drop two objects from a height and notice that, if they're exactly the same, density and shape and all sorts of other things, they may actually hit the ground at the same time. But then if you change them around so that one has a different density than the other one, the more dense object will actually hit the ground first. And then it turns out that your theory, although in general correct, is incomplete because you also need to take air friction into account. And then you sort of go through, prediction, experiment, adjustment in that, iterative cycle. And I hope that at least one audience member can see where I'm going with this now. I'm not looking at anyone in particular. Anyways, so this model of the scientific method is based on the ideas of Karl Popper, who was also an epistemologist or a philosopher of science back in the 20th century. And this model has been criticized for being overly simplistic, and people say, yeah, but science doesn't really work that way. It's much more sophisticated and messy and all of that. And I completely understand all of that criticism, but I'm trying to make a point here, and this will turn out, you'll see what the point is later on. But this is good enough, and I think, to a certain degree, we can argue that there's a grain of truth in this. The world is more messy, it's more sophisticated, we understand. Well, let's try to go with this and say, this is the scientific method. Okay, this is how we acquire knowledge. Right, so can we now answer the question, how do we know that our software works? Yes, let's get there. So I apologize for spending 35 minutes going, taking the long route around, but I think it's really important that you understand, what works in reality, because science and the scientific method has had, a couple of 100 years of lots of success. Just think about the recent, COVID vaccines that were developed in record time. That was based on, knowledge acquired by making experiments and understanding how DNA and RNA and such as, things work. So it's really important that we realize that that way of acquiring knowledge is really, really useful. Now, a long time ago, when I started out my career in software development, that's a couple of decades ago, the way that we would work would typically be in this thing called waterfall model that you probably heard about, where first of all there were some people who were paid much more than I was that would have go through a planning phase where they were thinking deep thoughts and coming up with all sorts of ideas, and then after they'd done that, they would hand over all those plans over to lowly programmers like me, and we would then proceed to go sit at our desk and write code. And we would write code, and we would write code, and we would write code for days, for weeks, for months. And granted, we'd do some casual, try, to compile the code and start the program and, just mess around with it a little bit in a fairly unsystematic way. But in general, we would just write code for months. And sooner or later, we'd reach a point where we'd say, okay, so now we think the code is ready. And you could go and try to adopt the previous explanation and say, oh, this is because we now have a good enough hypothesis that we believe the software works. Now, what really happens is you reach a deadline where, according to some Gantt chart, it turns out that, oh, the programming phase is now over, and we need to move on to the next phase. But anyways, what happens is that you hand over all of that software that you produced to a quality assurance department who then proceeds to test your code. So these people would have been busy already while we were writing code, and they would create plans where they would try to falsify the prediction that the software actually works. That's actually what they were paid to do. They would try to falsify that the software works. Essentially also try to find as many bugs as possible. That's what they did. And one problem with that approach is that this takes a long time, because these were real people who were doing things. So a test plan was a document that would contain a lot of smaller plans that said, all right, now go and start the program, and people would often print those plans out on paper, and they would have it on the side, and they would go, oh, start the program, okay, start the program, click that button, okay, click that button, okay, type this in, okay, now verify that the screen shows this, okay, does it show this? And then, if everything's okay, you'd flip the page over and you'd start a new little test case. But if it turns out that something is wrong, you'd file a bug report. And again, if you can imagine that you have real people sitting and doing this, it's not something that takes a couple of seconds. This is something that takes weeks, because you have hundreds, if not thousands, of test cases that you need to go through for any sort of sophisticated system. And then when that's over, what happens then is that all your illusions that the software ever works are completely shattered, because you have 1,000 bugs being reported, and now you have to go back and write some more code in order to fix all of those defects. And then once you've done that, you go back and hand your software over to the testers, who then go through that iterative approach. So even though we were, even in Waterfall, you had those small iterative things going on inside of those phases. But I want to spend a little bit of time on this thing about, the testing phase taking a long time. Because it was people who were involved. Now, so what this means is that in your organization, it would take weeks in order to acquire knowledge about the system. So you have this hypothesis that the system may work, but before you can't get your answer until a couple of weeks go by. And then you've gained some knowledge about the system, and you probably learned that there's a lot of problems with it still, and then you need to try to go fix that, and then you hand it over to the quality assurance department once more, who then have to spend a couple of weeks going through the same things again. And even the things that worked, they still need to check that these things still work, because there are these things called regression bugs, where you may have fixed the bug, but then it reappears later on. So they have to go through the full test every other time. So that just takes a long time. Now, if you're the only organization in your field of whatever it is that you do, this may not be much of a problem. But if you have some sort of competitor who figured out how to do this faster than you can do, now you have a really big problem. Because either they can actually, in the same time it takes you to gain a certain amount of knowledge about your system, they can gain much more knowledge, which will enable them to produce a product of a higher quality. Or they can produce a product of the same quality that you do, but in a shorter time, and they can outcompete you every other way, each of those ways. And we saw that happening in the 90s with various different software companies, which were really big in the 90s, but then got outcompeted because other competitors figured out how to do things in a better way. So we really need to figure out, or we needed back then to figure out, okay, how can we actually make that testing phase go faster? And then someone, sooner or later noticed that even though, these human testers were working according to a test plan, they were doing the same things over and over again, because it's very important that you have a consistent test plan. And also that test plan was basically just a series of steps, do this, do this, do this, do this. So this seems quite scriptable. It seems like something you can automate. So what happens if you automate the test? That sounds like a really good idea. All right, so let's try to do that. Now, how do you automate tests? Well, you typically write some code that now performs all the test cases that you need to go through. Okay, so now you have more code. So that now raises the problem. How do you know that works? Should you write tests of your test code in order to verify that your test code works? Is it going to be turtles all the way down? And obviously that's not going to work. So you need to figure out another way of solving that problem. And it's quite difficult, actually. This is a real problem, because there's research that indicates that the more lines of code you have in a code base, the more bugs you have, and that relationship is linear. And often test code tends to be quite substantial, so you actually have a lot of test code. So it seems like if you add more test code to a code base, you would be producing more bugs. See, that doesn't sound like it's a good idea, but it turns out that it works out anyway. And one of the reasons for that is that, first of all, this is not a universal single relationship. It is a general relationship in a specific code base, but the slope of that linear relationship may be different from one code base to the other. So what we'd really like to do is to say, can we change our code base so that it doesn't have that steep slope, but has this more shallow slope? That would be one thing where we could rescue this idea of adding test code. Now, the other thing that rescues us is that bugs tend to appear in clusters. Bugs cluster around certain parts of the code base, and you probably, if you've written any code for a long time, you probably realize that there are certain parts of the code base where it just keeps on bugs keep on being discovered in that part of the code base, and there are other parts of the code base where you rarely see a bug because it's simple. So, so even though we have this, on average linear relationship between, how much code you have and the bugs you have, it's an average number, but the average hides that there's actually some clustering going on. So if you can keep the test code simple, it's probably going to be okay. Okay, this sounds a little bit hand-wavy. You say it's probably going to be okay, and since I've been quite rigorous about talking about knowledge so far, you may not be entirely convinced. So we'll get to somewhere where we can be much more convinced, but that's the start of it. So let's try to figure this out. Why do we trust automated tests? And we can start out with the things that I've tried to outline already. You can imagine that you have some complicated production code, and I've tried to illustrate that by having a little graph here that basically this is just sort of like a mental, it's a little bit of a symbolic representation of what some complex code might do. And really complex code is much more complicated than that. So what you can say is that on the left-hand side there, you have some complicated code, and this might actually be where bugs cluster, where bugs keep, appearing. Well, can we get some... Are we back? No? This one? Well, I could keep talking because my monitor is working, but that's probably not going to be much of a benefit for you. Oh, there we go. Okay, let's see if that works. All right, so what we can do is we can write a simple example, and we can say, let's write a little bit of code that we start out in A. We have certain input parameters into A, and we'd expect that if we do that, we'll end up in C. Now, we haven't fully described what the production code is doing, but we've described parts of it. And then we add another one where we say, okay, if we still start in A, but we vary the input slightly, we would expect to start end up in G, and then we can do it one more time. We start up in A, and again vary the input slightly, and we'd expect to end up in H. And if we do that, we've actually, in this case, we've fully described the production code in the sense we have examples that takes us through all the different pathways in the production code, but the test code is much simpler. So we'd expect, because they're just linear, narratives from A to C and from A to G and so on, we'd expect them to belong to that, part of the code base where we don't have a lot of defects popping up. So that's part of the story. If this still doesn't sound quite convincing, we can do something a little bit stronger. We can write the tests first. Okay, so let's see where that leads us. Now, the reason why this is interesting is as follows. So now, this is now where you need to pay attention because things are going to get a little bit gnarly here. So at this point, we start out in a situation where we have no code at all, we have no production code, we have no test code, and we'd like to develop a system that has certain behaviors. So by writing the test first, the first thing we do is we write a test where we say, I believe that if I start out in A and with certain inputs, I should end up in C. Now, at this point, I can make a prediction. Now, this typically doesn't happen when you actually, this is sort of like an implied prediction. It's not that you formally do this, but the implied prediction is the following, and that is, if I now try to execute this test, I predict that it's going to fail. Now, notice that this is a prediction. It is a falsifiable prediction because I can execute the test, and if it actually succeeds, I have falsified the prediction that it was going to fail. And that, would tell me that I've probably not written the test code correctly. That's, if this test passes already, if this test already passes, there are two options. Either the behavior that I thought did not, already exist in the system was there all along, even though I didn't know that, or what is probably more likely is that, I thought that I'd written the correct tests, but it turns out that I didn't. So that's very important information. It turns out that it's easier to write an incorrect test than you would actually believe. So this gives us some knowledge about the test. But on the other hand, if I execute the test and if it actually fails, I have failed to falsify that it fails. Okay, so this is where you need to pay attention for, because that's a triple negative, but that's as good as we can get in terms of knowledge. I was predicting that it would fail, and I failed to falsify that. So it's not proof that it's always going to fail in all future, but it's just that, well, yeah, but we didn't see it succeed, so we have reasons to believe that we've done the right thing. So it's not proof that the test is correct, but it gives us confidence that the test is correct. And as I've tried to, do in this presentation, that, that's the best we can do. Build confidence that things are true. We can never prove things true. That's what we've done here. Now, what we now do is we go and implement the simplest thing that can possibly work in the production code. So we write just enough code that we believe that we can pass the tests. And now we can try to execute the code again. And notice there's another implied prediction here. The prediction is now that if I execute the tests are going to pass. So it's the opposite prediction, but it's still a falsifiable prediction, because if we run the test and the test still fails, we've falsified that assumption, and then we need to go back and figure out, okay, what went wrong. You know, we probably didn't write the production code so that it worked, but it might also turn out that there was some subtle thing about the test code that didn't work. But usually it's the production code where you've written some production code and you believe that it works, but it actually turns out that it doesn't. But on the other hand, you know, sooner or later you should reach a point where you can execute that test and the test is passing. So that now means we've failed to falsify the prediction that the test was going to pass. Okay, so again, a triple negative, and that's the best we can do. But that gives us some knowledge about the system, the entire system. We've now gained knowledge about why we can trust the tests, and we've gained some knowledge about why we can trust the production code. We have reasons to believe that these things are working in a useful way. And that's the best we can do. And now, from here on, we basically just repeat the procedure. So let's see if my clicker works. We write another test. We make the same implied prediction that if we run it the first time, it's going to fail. And we observe that this is the case. We then go and add some production code and watch the test succeed. And now again, we've failed to falsify our predictions, which means that we have reasons to believe that the system is actually congruent with the model of it that we have. And we can repeat that a third time in order to fully develop the system. My clicker is not really going where I want it to do. And then we can implement the thing, and we can run the test again, and then we'll see the test succeed. So does this seem familiar in any way? Does that remind you of anything? So basically, this is that iterative approach that we had before, where we make a prediction, then we perform an experiment, then we make an adjustment. Oh, this goes the other way for you. And then we go back and make a new prediction, and we make a new experiment, and we go and make a new adjustment, and then we keep going on in that circle. It's just that when we do it in programming, and when we do it with automated testing, we don't call it that, we just call it the red-green refactor cycle. And it's a foundational iterative process of doing test-driven development. So really, the point that I've been trying to make all along is that TDD is the scientific method. And I think this is really important, because I often run into organizations that tell me that they can't do TDD, or I meet experienced software developers who tell me that they can't do TDD, and it's often something like, yeah, it doesn't work in the real world, or it doesn't work in our organization, or in the field of whatever it is that people are working with. It doesn't work in the real world. And it's funny, because it's just the scientific method, and the scientific method is this far superior way of producing knowledge. There's basically no competition to the scientific method. I believe that the reason why this doesn't work for quite a few people, it's not that it doesn't work. It's like, science is hard, and it's really difficult to get it right. It's much more easy to get science wrong than it is to get it right. But if you want to do something that is methodical, that is predictable, that is actually proven to work in overall epistemology, and you want to apply all of the knowledge from a couple of hundred years of what actually works, and you want to apply that to your software process, you should really try out test-driven development. It's not the only thing that works, but this is a really interesting approach. So I think it's a very interesting realization to know that it's actually the scientific method. It's the same knowledge acquisition paradigm that you're in. So the point is really, if you're a programmer, you should be doing this. If you're a manager, you should let your programmers do this, because that is what produces predictable outcomes. So thank you for listening to me.
Thank you very much. Really insightful. I think I just want to mention one of the topics that we discussed about during the panel. Most of the time when people are building new frameworks, maybe they don't spend enough time trying to really understand those that exist and whether or not they fit the bill and could actually tap on that knowledge. Same thing with Agile and all the spin-offs from Agile. Maybe the core was not well understood enough so that then people started to build all sort of side frameworks. Yeah. And the same thing with TDD and BDD, right? Once you don't understand, it's easier to fight against it and say, well, capitalism is eventually going to fall. TDD is not always working and things like that, rather than trying to really understand and figure out what's not acceptable or what's not functioning in your own organization. Let's see if we have any questions from the audience. Yes, we have. Do we have a microphone? One is enough, thank you. More fitness after lunch.
So I like very much the presentation. One question that popped into my mind during it is that all this architecture and structuring the code, it's something that's things that we do to manage the complexity that is there. And if you migrate to large language model and to manage the complexity in order to be like human readable, maintainable, to extend it and so on. If we go to generated code, then it means we don't have the problem anymore because it's no humans that would need to understand it. Let's keep it like that theoretically. So question is, do you think that enabled by some TDD evolved version, TDD 2.0 for large language models auto-generated code, do you think that we can get rid of actual code, which would be kind of intermediate representation of what the machine should do, means to generate from language something, doesn't matter what, be running on the hardware architecture, yeah, and then tested, certified, whatever by TDD 2.0. Would that make sense for you?
The thing that I'm worried about is basically just, I can definitely imagine a world where you'd have some sort of automated system where you could give it a description of what it is that you want it to do, and then it would produce software that does that. And whether it actually does that by writing Python code or C code, or whether it just goes straight to something that is, machine instructions, it doesn't really matter. What really matters is that, again, you have the same problem as you have with communicating your software requirements to a programmer. Does whoever if you're handing over those requirements, were they correctly understood? And I think that's, again, this is the epistemological challenge here. So as I think it was Kevin Henney that said something like, if you, the act of actually being completely unambiguous in your specification and the act of programming is the same. If you have a way to specifying unambiguously what it is that a computer should do, that is code. This is basically what code does. So, so that means if you do that, you still have programmers, even though you then have a translation step where some automatable machinery turns that into actual executable code, but that's one thing. But then again, if you don't know how to do that, if you're a business user, someone else who just comes by and say, I'd like the system to do something, you still have that verification problem. How do you know that it actually understood what you meant correctly? So can we envision something like where we could say, could we have a system that then goes through this prediction experimentation phase? Okay, so this is the first time I actually think of this, but maybe we could have some sort of two adversarial systems where one is making the predictions and then we have the other system that actually performs the experiment, and we can somehow have them fight it out. I don't know if that's going to work. I know adversarial AI is a thing, but it's not really, AI is not my area of expertise at all, so I don't know. So I'll be keen on seeing how that actually turns out. I'm not trying to make any predictions here, but I'm just like, until that day happens where all of this automation happens, I think it's really important to realize that There are processes that are sometimes being shoved away as being hippie agile processes that Ken Beck and other hippies came up with. Ken Beck is not a hippie, but still, and it doesn't really work in the real world. It doesn't work in banking or in oil or whatever. But what I'm really trying to do here is to say, I believe that this is the most fundamental way to acquire knowledge about your software systems that we know of at the moment. Or agile processes in general, not agile theater, but just the original ideas about actually getting going through iterations to have feedback. Dan, did you have? I'm going to give you a copy of the book because that was a great question. Dan, did you have a comment there? Yeah. Someone else? Was that a comment or was it someone else? You have a question. Okay, fair enough. Let's go for another question first.
Actually, it's not a question. It's more of a comment.
Where's the person?
It's.
Thank you.
So it's. Incidentally, I happen to know a thing or two about the philosophy of science, and actually, you mentioned something really interesting with regards to testing the tests, and it's actually goes deeper than that because, the theory that you can only disprove theories in science was proposed by Karl Popper, but actually since then there's been new things. I mean, in the 80s, and there's maybe you would be interested in looking up the Quine-Duhem thesis that says you actually cannot test, you cannot verify a single hypothesis alone. It has to be a number of hypotheses all linked together, and if one is false, something is false in one of them. So it's the same exact thing with the tests. So if the test fails, maybe the code is wrong, but you don't know if maybe the tests are wrong. So, TDD and science might be more linked than.
I didn't know that. That sounds interesting. Well, anyway, I think you probably just by sheer luck of being the second person who dares to comment. You're a long way off, but could you come and pick it up afterwards? I'll be happy to give it to you. I am out of books now, but I'm happy to take more questions. Yes.
So. Can the pendulum swing too far the other way? Can we get too wedded to the scientific method, like it's some kind of totem? And maybe are there other ways of writing good software that would go hand in hand with that or alongside of that? Mm-hmm. Or is it that the scientific method is the ultimate purity and that should be what
I'm glad I'm glad you're asking this because that's actually not what I mean here. I'm not an absolutist in any ways because I do understand that there's a lot of other things that we need to take into account as well, like the readability. I haven't really talked about readability of code at all. We talked a little bit about that in the panel here. So my agenda with this particular talk is just that I wanted to address this very common resistance that I run into when I talk about TDD and agile methods in general is that people seem to find it unscientific somehow or not like engineering. And the point that I'm really trying to make here is that it doesn't get much more scientific than this. So if that's your reason for not liking it, is because you completely misunderstood the process. And that's really my point here. But no, it doesn't stand alone. There are lots of other things that needs to go into a good engineering organization as well. Yeah. So good. I'm glad you asked because otherwise people might have missed that. Yes.
Hello.
Hello.
Technologies are very fast now, so everything is changing faster than 10 years ago.
Yeah.
How can we trust specific technologies now, because they're appearing as mushrooms, and how can we identify the truth for them? Like, you need to see if something is new, do we trust it? How deep should we go with that?
Yeah.
In programming, but even in reality, because you started with reality things, like if we see now a lot of Romanians hate electrical cars, yeah, EV, because pollute more than gas and things like that. So we still think behind, but now if the technologies are appearing and appearing and appearing, how we identify the truth between, or how we choose.
Yeah, I could maybe make a consultancy business out of answering questions like that. Oh, by the way, I am an independent consultant. You should hire me. Now, I don't really know how to answer that. I mean, the problem, again, is that knowledge is, the kind of knowledge that I'm working with here is basically generated in hindsight. You know, you make observations of what happens, and then you draw conclusions out of that. You can make predictions, but the predictions are only verified or the opposite after the fact. So, you know, I could tell you a lot of crap about saying, okay, this will happen in the next 10 years, but it's just going to be my, you know, even if I'm right, you have no reason to believe me right now. No, I mean, if I'm going to make a prediction about what's going to happen in the next 10 years, I can promise you already now that I'm going to be bullshitting. But, you know, but if I didn't tell you that and I told you something, do you have reason to believe that I'm right? And you shouldn't have. You should be skeptical because who knows? That doesn't mean that you can't get some good insights from people who have, you know, reasons to believe that they know what they're talking about, which I don't really in this space here. But all of these things that pop up, you know, most of them are going to fade away again. That's just, you know, at least again, if we learn from. So I think what was the name, George Santayana, something like that. It says, you know, those who will not learn from history are doomed to repeat it. So what we see a lot of things going on at the moment is that there are a new generation of young programmers who are coming around who are inventing the same things that were invented 20 years ago. And 20 years ago, the programmers, you know, I was young 20 years ago, we were reinventing what was invented 20 years before that and so on. So we have this very short time frame. So I think the best thing we can do is try to, you know, learn a little bit more from the past. I think Alan Kay has a very nice quote where he says something like, you know, programming is essentially pop culture. We're so obsessed with all the new and shiny, but we forget what happened 2 years ago. And yeah, I think we should have a little bit of a better, you know, time horizon going backwards, if you will. But going forwards, you can make bets on certain technologies, but there's no certain knowledge there. So again, you know, to quote Socrates, all I know is that I know nothing. So it's not really a good answer to your question, but that's what I can do. So sorry about that.
Maybe expanding on what you already presented, Mark, acquire knowledge that will lead you to the right questions, that will help you validate or invalidate everything that you're exposed to. We have one more question here.
Hello.
Last one.
This might be a bit of a loaded question. So I'm a bit curious, if you're writing a prototype or just a throwaway code, and you know that you're just writing it just to validate an idea, and it's a throwaway bit a piece of code, and most probably you will refactor it and rewrite it. And do you still use the test-driven development, knowing that it's I think I already know your answer, but knowing that it's a bit of an overhead to do the test-driven development?
I would probably typically not do TDD in that case, but again, because what you're embarking out, when you're doing a prototype, is a different kind of experiment, but it is also an experiment. Now, your hypothesis or your prediction is that I believe that a certain approach, you know, using a certain technology or using a certain algorithm, I believe that that is actually going to solve my problem, but I'm not sure. So you are entering into that task with a very open mind, actually, because that's what a prototype is. You want to check whether or not something seems, you know, like a good approach or not. And then if you want to do it correctly, you should have some sort of evaluation criterion that is established up front, where you say, if I can't get it to do this particular thing, then I'm going to give it up. And again, that doesn't give you knowledge, it doesn't give you certain knowledge, but it just gives you some idea about, well, I tried to spend 2 weeks on this, I couldn't make it work. It's probably because it doesn't work, but maybe it's just me. But again, it's a different kind of science experiment, if you will, but it's still a science experiment. So I think it's a little bit more coarse-grained, but since the purpose is, it's a different kind of experiment, so do you need to then make small experiments within that bigger experiment? And it's not always helpful to do that. And if you realize that that's not helpful, then just don't do TDD there, because on the other hand, you gain some other knowledge from that experiment, and then hopefully you throw away that code, or you don't, at least you don't copy it into production, right? So what I usually do is when people want me to do a prototype, I usually say, I'll be happy to, and I'll write it in Haskell. Because then I'm absolutely certain that no one will ever put that into production. So that's a very effective way of preventing that. Okay, I'm rambling, I'm sorry. I hope that was a good enough answer to that question. So yeah, that was the last one?
Yeah, that was the last one. Thank you very much for your time. Thank you very much for all the great information. So we're looking forward for the next time you're going to be on our stage, and we wish you good luck with the personal matters, and hope to, you're going to get in time and things are going to settle as you want.
I hope so.
Okay, let's give a big round because it was an amazing presentation. Thank you.